What is the primary benefit of learning rate warmup, according to the paper?
The primary benefit of learning rate warmup, according to the paper, is to allow the network to tolerate larger learning rates than it otherwise would have. This is demonstrated through systematic experiments across various architectures, initializations, datasets, and optimizers. The warm-up phase gradually reduces sharpness, guiding training towards flatter regions that can accommodate higher learning rates. The paper emphasizes that the main advantage of warm-up is to enable the network to withstand larger target learning rates, making hyperparameter tuning more robust and extending the range of optimal target learning rates. Additionally, warm-up helps prevent training failures and performance degradation by stabilizing the training dynamics and keeping the network away from the divergence boundary.
Can you explain the warm-up mechanisms of gradient and adaptive methods based on the paper?
The warm-up mechanisms of gradient and adaptive methods, as explained in the paper, involve gradually increasing the learning rate during the warm-up phase to allow the network to adapt to higher learning rates. For gradient methods like stochastic gradient descent, SGD, warm-up is tied to sharpness dynamics, where sharpness determines the instability threshold eta_c. As the learning rate increases, training instabilities can be triggered, leading to temporary loss increases, and sharpness decreases to restore stability through a self-stabilization mechanism. This process guides training towards flatter regions that can handle higher learning rates. The paper distinguishes between natural sharpness evolution and warm-up-induced sharpness changes, highlighting cooperative and competitive dynamics between the two. In the case of adaptive optimizers like Atom, warm-up focuses on reducing the preconditioned sharpness to prevent large instabilities and training failures. Warm-up allows the network to collect accurate gradient statistics before using larger learning rates, enhancing performance and stability. The primary goal of warm-up across both gradient and adaptive methods is to enable training at higher learning rates by annealing sharpness or preconditioned sharpness, ultimately improving model performance and preventing training failures.
How is the target learning rate reached earlier by setting the initial learning rate to eta_c?
Setting the initial learning rate to eta_c allows the target learning rate to be reached earlier by inducing a loss increase and sharpness decrease right from initialization. This approach initiates the primary effect of warm-up sooner, facilitating training at higher learning rates. By starting with eta_text init equals eta_c, the modified warm-up schedule reaches the target learning rate in t_text reach equals t_text wrm, 1 nicefrac eta_c eta_text trgt. Steps, saving t_text wrm, nicefrac eta_c eta_text trgt. Steps. This strategy leads to computational savings by reducing the warm-up duration needed to achieve the target learning rate. The net computational savings, accounting for the additional forward passes required to estimate eta_c, is calculated as t_text save equals t_text wrm. Left nicefrac eta_c eta_text trgt. Right nicefrac t_text fp2. The approach of setting eta_text init equals eta_c allows for a more efficient warm-up process, enabling the network to adapt to higher learning rates sooner and optimizing the training dynamics effectively.
What is the proposed method GI Atom, and how does it improve over standard Atom?
The proposed method GI Atom initializes the second moment using the gradient squared. v_0 equals g_0 to the power of 2 in the Atom optimizer. This initialization strategy eliminates the need for a bias correction and can be viewed as standard Atom with an automated warm-up schedule. GI Atom significantly reduces the initial preconditioned sharpness by around 2 orders of magnitude at initialization, preventing large catapults that can lead to training failures. By starting with a lower preconditioned sharpness, GI Atom improves performance across datasets and prevents training failures by pushing the training failure boundary to higher target learning rates. This method consistently outperforms standard Atom and provides a more stable training process by addressing the issue of high initial preconditioned sharpness, which can cause instabilities and hinder training progress.
Explain the persistent catapult warm-up strategy and how it compares to linear warm-up.
The persistent catapult warm-up strategy aims to progressively reduce sharpness during training to facilitate higher learning rates without the need to specify a warm-up duration. The strategy involves inducing catapults by increasing the learning rate to the upper instability threshold, waiting for the loss to fall below a stable reference point, and repeating this process until the target learning rate is achieved. This adaptive approach utilizes local sharpness information to automatically adjust the warm-up rate, making it more efficient and effective. In contrast, linear warm-up involves a fixed schedule where the learning rate is increased linearly from 0 to a target value over a specified warm-up time. The persistent catapult warm-up strategy eliminates the manual tuning of warm-up duration, providing a more adaptive and potentially parameter-free approach to warm-up. It allows for training at higher learning rates without the need for explicit warm-up duration setting, making it a promising alternative to traditional linear warm-up strategies.
What are the limitations of the experiments conducted in the paper?
The limitations of the experiments conducted in the paper include the fact that they were carried out on relatively small-scale datasets and models. This suggests that further investigations are needed to understand the generalizability of the findings to larger-scale settings. Additionally, for the Atom optimizer, the study did not explore the dependence on hyperparameters such as beta_1, beta_2, and epsilon. This lack of exploration could impact the robustness and applicability of the results to a wider range of scenarios.